Heat capacity of a spin system. A system of capital N atoms, each having spin 1/2 and a magnetic moment mu0, is located in an external magnetic field B and is in equilibrium at the absolute temperature T. Focus attention on the spins only and answer the following questions. A. Without doing any computations, find the limiting values of the mean energy of the system as temperature goes to 0 and at very high temperatures as T goes to infinity. So let's start with this. Now I have capital N spins, capital N atoms each having spin 1/2, magnetic moment mu0, that is the magnetic moment of each spin. External field is B, and we have the temperature, absolute temperature T of the system. Now the net magnetic moment that is pointing along the field direction, as I'm assuming that the magnetic field is pointing up, will be number of up moments minus number of down moments multiplied by mu0. So N is number of up moments, N prime is number of down moments. And the energy of the system is a function of m. It is minus n minus n0, n prime, mu0 times b. So this is the total energy of the system. And if I concentrate on the spins, individual spins, I find that they have two energy levels. So for individual spins, I can see that I have two energy levels here. There is the energy level epsilon plus, which is minus mu0b. There is the energy level epsilon minus, which is plus mu0b. And I'm assuming that the magnetic field B is pointing up. And the difference between these two energy levels, delta E, is equal to 2 mu0b. So when we have the thermal energy approximately equal to delta E, 2 mu0b, so that the critical temperature is 2 mu0b divided by K, there will be significant transitions between these two energy levels. So without doing any computations, what is our expectation for the occupancy of these energy levels? So I can argue that as T goes to 0, the system will reach its ground state. So the system will be in the lowest possible energy, will have the lowest possible energy, that is the ground state, and so that the mean value of epsilon will become minus mu0b. And on the other hand, as T goes to infinity, I expect that I have the most random distribution of moments. So n will become n prime, and this will be equal to capital N over 2. So I will have half of them with up moments and half of them with down moments, so that on average I will find epsilon bar will go to 0. And since the total energy E bar will be given by the number of atoms times mean energy per moment, this will be equal to, or it will go to minus n mu0b in the limit temperature goes to 0, and it will become 0 in the limit temperature goes to infinity. So I have the most random distribution of moments, half of them up, half of them down as t goes to infinity, and I have minus n mu 0b, the lowest possible energy as t goes to 0. So if I plot this qualitatively, this is what it would look like. So this is E bar as a function of t. So let me do this properly with the origin being at 0 point. So let's put it like this. So initially at 0 temperature we have minus n mu 0b. So let me label minus n mu 0b here. So, and as t goes to infinity, so we start here, as t goes to infinity, we reach 0. So this would be the qualitative plot. And where does this transition occur between these two limits? This is the critical temperature, which is roughly of the order 2 mu 0b divided by K. Okay, now without doing any computations in part B, find the limiting values of the heat capacity at constant magnetic field as t goes to 0 and as t goes to infinity. Now the heat capacity, on the other hand, is given as the derivative of the mean energy with respect to temperature when all the external parameters are fixed. I call all the external parameters x. So looking at my plot, it appears that the derivative c of t will approach 0 as t approaches 0, and it also approaches 0 as t goes to infinity because I have two limiting values, constant values, and in the middle I have for t less than Tc, so, or let me say for t is slightly less than Tc, Tc minus, I will have a positive C, and when t is equal to Tc plus, I will have a negative C value. That is not right. So I will have a negative slope and or a decreasing slope rather. So it's going to be, and when t is equal to Tc minus, C is increasing, and when t is equal to Tc plus, C is decreasing. So if I have a qualitative plot of C as a function of t, C as a function of t, this would look like this. I will have a sharp peak, and this would be around the critical temperature, which is 2 mu 0b over K. The heat capacity would be reaching its maximum value. So let's go to part C. Calculate the mean energy of the system as a function of temperature T. Make an approximate sketch. So now we're going to do the quantitative calculation. So we have the mean energy of the system for one spin. It's going to be equal to sum over r epsilon r e to the minus beta epsilon r divided by the partition function z, where z is equal to sum over r e to the minus beta epsilon r. So this would be equal to for the E plus level minus mu 0 b energy corresponding Boltzmann factor e to the beta mu 0 b, and then we will have plus mu 0 b e to the minus beta mu 0 b divided by the partition function, which is e to the beta mu 0 b plus e to the minus beta mu 0 b. So you can see that the mean energy per moment will be in minus mu 0 b parentheses I call alpha beta mu 0 b. This will be e to the alpha minus e to the minus alpha, e to the alpha plus e to the minus alpha. So I see that the mean energy per moment will be minus mu 0 b tangent hyperbolic alpha, which is tangent hyperbolic beta mu 0 b. Now the total energy will be equal to capital N epsilon bar, which will be minus capital N mu 0 b tangent hyperbolic beta mu 0 b. Well, since beta is not given, we are given the temperature T, we should write this answer as mu 0 b divided by Boltzmann constant times temperature. So this will be the total mean energy of the system. So we will now make an approximate sketch of E bar versus T. So let me look at the two limits here. As T goes to 0, alpha, what I called alpha, is going to infinity. And what happens to tangent hyperbolic in that case? So I have e to the alpha minus e to the minus alpha. E to the minus alphas would disappear. Tangent hyperbolic alpha would become e to the alpha minus e to the minus alpha divided by e to the alpha plus e to the minus alpha. So these two will cancel. So this is becoming 1. So what do I see? E bar is becoming minus capital N mu 0 b. On the other hand, as temperature goes to infinity, alpha goes to 0, and tangent hyperbolic alpha, which is e to the alpha minus e to the minus alpha divided by e to the alpha plus e to the minus alpha, is going to be 1 minus 1. So this would become 1 minus 1 divided by 2, so it's becoming 0, so that the mean energy will become 0 as expected. So in between I would have the transition. So my approximate sketch for E bar as a function of T would look exactly like what I have done in my qualitative arguments. It would start at minus N mu 0 b, and then it will become 0 at high temperatures. So this would be the behavior, expected behavior of E bar as a function of T. So it matches with what I had in part A. Calculate the heat capacity of this system, make an approximate sketch. So let's look at the heat capacity. Now heat capacity, remember, is the derivative E bar with respect to temperature when all external parameters are fixed. So my expression for the mean energy is minus capital N mu 0 b. So I have the derivative with respect to temperature of minus capital N mu 0 b tangent hyperbolic alpha. So this is going to be minus capital N mu 0 b, because tangent hyperbolic is a function of beta, so I will have del beta of tangent hyperbolic alpha, and then del beta del t to get the temperature derivative. So the heat capacity will become then minus capital N mu 0 b. Del beta del t is minus 1 over k t squared, Then I have the derivative with respect to beta of tangent hyperbolic alpha. So the derivative with respect to beta of tangent hyperbolic beta mu 0 b. So here this is going to become, two minuses will become plus, capital N mu 0 b. If I multiply the top and bottom with k, this is going to become k squared t squared. And the derivative with respect to beta will give me a factor mu 0 b, and the derivative of tangent hyperbolic will give me secant hyperbolic square beta mu 0 b. So that's the reason why we're using this tangents and sines and cosines, etc. here. So remember, tangent x is sine x divided by cosine x. If you take the derivative of tangent x here, you get cosine square x plus sine square x divided by cosine square x, which is secant square x. So indeed, that's what is happening here. And 1 over k square t square, on the other hand, is going to be beta square. So n, capital N k, mu 0 b beta square secant hyperbolic square beta mu 0 b, or I can write it more explicitly like this: capital N k mu 0 b over kt squared secant hyperbolic squared mu 0 b over kt. Now, in order to determine, so basically we can say that this is our answer for c as a function of t. Now I'm going to make an approximate sketch of this. So for that reason, I'm going to substitute for secant hyperbolic 1 over cosine hyperbolic. So secant hyperbolic x is 1 over cosine hyperbolic x, which is 2 over e to the x plus e to the minus x. So my heat capacity can be written as capital Nk mu 0 b over kt squared, and then I have 2 square, it's going to become 4 divided by e to the x plus e to the minus x, so it's going to be e to the mu 0 b over kt plus e to the minus mu 0 b over kt parentheses squared. So I want to make an approximate sketch of this. So what happens to c as t goes to 0? As t goes to 0, so let's take a look at the behavior here. 1 over t will become infinite, so I have in the c function there is a beta square, so c is going as beta square and secant hyperbolic square of beta, so the temperature dependence is here, and therefore if I look at what happens to secant hyperbolic square, so I need to look at the behavior of cosine hyperbolic. So as t goes to 0, beta goes to infinity, so the second term, e to the minus x term, would disappear. So you would get 2 over e to the x, where x is our beta here, so it's going to be 2 over infinite basically. So we have a beta, so we can basically replace the secant hyperbolic x. So let's do this in a different page. So secant hyperbolic x, as x goes to infinity, will be e to 2 divided by e to the x plus e to the minus x. E to the minus x will become negligible, So 2 divided by infinity, it's going to be, so it's basically going to 0. But on the other hand, I have a beta square here. So my heat capacity would go to beta square divided by e to the beta in this limit. So the limit as beta goes to infinity, beta square over e to the beta using L'Hopital rule would become the limit as beta goes to infinity 2 beta over e to the beta, which is the limit as beta goes to infinity 2 divided by e to the beta, which is 0. So I find that the specific the heat capacity will go to 0 as t goes to 0. On the other hand, as t goes to infinity, beta will approach 0. So what happens to secant hyperbolic x when x goes to 0? So it's going to be 2 over 2, which will be approaching 1. So then the heat capacity would go as beta square only, where beta is approaching 1, so C would be approaching 0. So qualitative plot for heat capacity would be as follows. Heat capacity as a function of T, it has to approach 0 as T goes to 0, and it has to approach 0 as T goes to infinity. So at a critical temperature, which is 2 mu 0 B over K, it's going to have a maximum in the heat capacity. So basically here we also see an application of the Schottky anomaly for this spin system. So let's review what we said. We have capital N spins, N moments pointing up, N prime moments pointing down. They have energy levels minus mu 0b and plus mu 0b for each spin, and I've assumed the magnetic field is pointing up. When the thermal energy matches the energy difference, there will be significant transitions. So the critical temperature is 2 mu 0b over K. As the temperature goes to 0, the system should be in the ground state, so I have the lowest possible energy minus mu 0b for each spin, and as t goes to infinity, I should have half of them pointing up, half of them pointing down, so that I have the most random distribution. So epsilon bar will be 0, so the total energy would change from minus capital N mu 0b and plus and 0, with a transition occurring roughly around 2 mu 0b over K. The heat capacity, the derivative of the mean energy with respect to temperature, would approach 0 in both limits because I have a constant value at these two limits. However, I see a transition at the critical temperature, so there should be a change of slope in the E bar versus T curve. So here I have the heat capacity increasing, so I have an increasing slope and a decreasing slope as I go from 0 to Tc and Tc to T. So I can see that the heat capacity, because I have an increasing slope and a decreasing slope, will give me this type of behavior qualitatively. Now I calculated the mean value of the total energy. Epsilon bar is capital N mu 0b tangent hyperbolic. This is something we have done before. And we see that the limits also give us the same answer for E bar. And for the heat capacity, we've taken a derivative of this with respect to temperature, and with our explicit calculation, we have found that this heat capacity is behaving as beta square secant hyperbolic square beta. Well, there is a constant in front of beta, but just to look at the temperature dependence, it's enough. So if you wish, we could put a constant A here, doesn't matter. And we find that indeed the behavior is the heat capacity becomes 0 in both limits, t goes to 0 and t goes to infinity, giving us the Schottky anomaly. At the critical temperature, we have the maximum value, which is at temperature 2 mu 0b over K.